The structure of hydrocarbon A is shown below. A. Hydrocarbon A can be reacted with bromine in the presence of ultraviolet radiation to prepare CH3 brackets 2 CCHBr CH3. What is the systematic name for CH3 brackets 3 CCHBr CH3? So firstly with this question, let's draw out the structure we need to name. So drawing this, we're going to add the bromine to carbon number 2. So we have our 3 methyl groups, our carbon chain, and then Br for bromine. Now we can start to name this. So we always start with the highest priority group, which is going to be bromine, and that's on carbon number 2, so we go 2-bromo. Then we look at the side chains. So we've got 2 on carbon number 3. We have 3,3-dimethyl. And finally, we need to look at the longest carbon chain. So that's going to be 1, 2, 3, 4 carbon lengths long, which is butane. So this is going to be our full systematic name for the structure, 2-bromo 3,3-dimethylbutane. And you need to write this systematic name in order to get the mark for this question. B. CH3 brackets 3 CCHBr CH3 has stereoisomers. Part 1. Explain the term stereoisomers and name this type of stereoisomerism. So this question relies on recall. And if you got this question wrong, it's worth noting this on a flashcard so that you can revisit it and learn the set phrase to write. So the explanation that they want for what a stereoisomer is that there's a same structural formula but a different spatial arrangement of atoms. You could have also said a different arrangement of atoms in space. So to help us identify the type of stereoisomer in this compound, let's draw it out again. So we have our 2 side groups and the beginning of our carbon chain, our 4 carbon chain lengths, and then our bromine. So the type of stereoisomer here is an optical isomer because we have what's called a chiral carbon center, where we have 4 different functional groups attached to a carbon. So this type of stereoisomerism is called optical isomerism when you have a chiral carbon. So that's what we can put here. We can put optical for the type of stereoisomerism. And to get the mark for this question, you must have the correct explanation, which I've written here, and you must have said optical. You need both bits to get the mark. Part 2. Draw 3D diagrams for the stereoisomers of CH3 brackets 3 CCHBr CH3. So the key here is that they want 3D diagrams, which means we're going to need to use wedges. So drawing out our structure again, just so that we know where the chiral centre is here, and then we can label our chiral centre with an asterisk. So carbon has 4 groups attached to it. We have an invisible hydrogen here because in skeletal diagrams you don't draw on the hydrogens. But there are 4 different groups attached to this carbon. And because there are 4 groups in carbon, we're going to have tetrahedral wedges. So if I draw the dashed wedge here and then the solid wedge, we'll have bromine on the top, our methyl side groups here, where we have CH3 and 3 of them. Then we're going to have our hydrogen and our CH3. So as we can see, this big methyl side group is this component of our 4 groups. Then we have our bromine, we have our hydrogen, and then this is going to be CH3, which we've written. Then, because it's optical isomerism, we have a mirror image, and that's going to be our other stereoisomer. So we have the same layout, but our wedges flip. So instead, our dashed and our solid wedge are going to be on the left. But we have the same groups attached, so we have the CH3, the hydrogen, the bromine, and then our CH3 also attached. So these are our 2 different stereoisomers for our compound that we've been given. And to get the mark for this question, you need to have both 3D diagrams. If you've only drawn one, that's going to be 1 mark. To get 2 marks, you need to draw both of them. C. Complete the table to show the mechanism for the reaction of hydrocarbon A with Br2 to form CH3 brackets 3C CHBr CH3. Use skeletal formulae for all organic compounds. Use dots to show the position of unpaired electrons. So this question is using a mechanism called free radical substitution. So a common example of free radical substitution would be using chlorine. In this case, we're using bromine, but you might have seen this done with chlorine in class. Now, at the end of this, we're supposed to form this product. So we need to double check that we've done it right if we do form this product. So free radical substitution consists of 3 steps or 3 stages: initiation, propagation, and termination. Here we're only asked to show initiation and propagation. So initiation is when you form your radicals. So you'd start with your bromine, and then under UV you form 2 bromine radicals. So you could write UV on the arrow here. That's not going to do you any harm in this question, and it is how you form the radicals. You need this ultraviolet light to form them. Then with propagation, you start by adding a bromine radical, and then you get hydrogen bromide, but then you'll get a radical of your hydrocarbon. So you'll have the radical where you want to add your bromine at the end, because in the next stage you take this radical and then you're going to add Br2. So the bromine can then be added to where your radical part is on your hydrocarbon, and then you can get the product that you wanted at the end, where you've got your bromine on carbon number 2, and then you're left over with a bromine radical. So here are the initiation and propagation steps. Termination, all it is when you add 2 radicals together. So that could be 2 bromine radicals and you'd form bromine again. You could form a bromine and this radical, so you would form your product again. Or you can take 2 of these hydrocarbon radicals and then you just make a very long hydrocarbon chain. But that's all that termination is. But this question does not ask you for termination, only initiation and propagation. To get the 3 marks for this question, you get a mark for your initiation step, and then you get a mark for each line or each equation in your propagation step. D. State 2 limitations of using radical substitution in organic synthesis. So our first limitation of radical substitution is that you can have further substitutions, and you keep substituting on your hydrocarbon chain until all the hydrogens are replaced with a halogen. Also, your second limitation is that the substitution could happen at different positions along the chain, so you might not always get the product that you want coming off at the end. So instead of saying further substitutions as the first limitation, the mark scheme would have also accepted saying produces different termination products, or more than one termination step, or a mixture of products are formed. So either of these 4 statements would have gotten you the first mark. Then your second mark, you have to say substitution at different positions along chain.